Okay, so today let me talk about more about answering the solutions. So first, let me give you a proof of this theorem I stated last time. So I restated here. So I guess give a proof without the full details, but a lot of details. So I hope you still remember this. So anyway, if you don't remember, here it's a statement again. So I want to prove existence of asymptotic shrinking soliton. So soliton, by soliton I mean a solution of Ricci flow which satisfies these equations. And there's so this equation is actually equivalent to you can say all the GT is obtained by pulling back a fixed metric, and then this fixed metric satisfies this one equation. So equation here is actually just so equation star is only basically for one particular t. Okay, for all others are derived. So if you integrate this, you see here lambda here is in this case, because this sign of here, this lambda is actually less than 1, so which I forgot to mention last time. So this lambda is strictly less than 1. That's why it's called shrinking, because once you increase the t here, so this size of this metric gets shrunk. So you can easily see from here that this solution exists for all time. So namely, giving any solution of this star for say t equal to -1, then you can if you then you solve these ordinary differential equations to find the integral curve of this vector field given by a gradient of f. So then you find the family of diffeomorphisms and you probe back, and lambda can be easily solved from here by checking on the volume. So then you will find answering the solution. So Ricci solitons certainly are a special kind of answering the solution. So the essence in this proof is I want to do two things. First, I want to make sure this has a limit. Okay, so in order to do that, I need to bound the curvature of this. At least I need to bound the curvature of this metric uniformly for any points within a finite distance from this base point. So then, after verifying that, so then I can take a limit. After taking a limit, I know another thing is one we need to prove is say limit is a soliton. So we need some actual things. So soliton in some sense is like a homogeneous, like a solution with certain homogeneity. Okay. So now let me start with a proof. The first things step 1. We observe the following thing. We need to, namely, I need to bound the curvature of this. How do I bound it? So let me recall a hierarchy in the quantity. So let's I claim first step proof. So let's let's recall the hierarchy in the quantity. Recall. So hierarchy has a following. If you have a minus dr d tau, okay, and minus tau 0 of tau of r, okay, So where this is true, where this tau is bigger equal to tau 0. Of course, in our case, tau is always negative. Okay. So here you can rewrite this as follows. If you rewrite this, is okay. So tau here is minus t. So this one is basically says this term here is basically says r of t minus t0. Okay, minus t0. So and this is just dr dt. So if you write in this form, if you replace these two terms by this, then that's exactly what Halak inequality is. Okay, so we just put in this form because. So once I have this, then I recall what is h. The h which we use when we estimate the length functions. What h is actually is this term. Okay, so this is true for any vector field. So now if x is a derivative of L geodesics, is tangent of L geodesics, then what we get is this. So plus twice of dr of x plus 2 Ricci of this. So this is by definition hx. Okay, for this particular vector field, which gamma is any L geodesics. So this, if I can rewrite this as a minus, and so I plus. So this is gamma 0r, okay, of r, and minus this term. So then plus something which involved in the definition of in the formula of Hamilton-Halak inequality. So this should be equal to that. Okay. So except this term, all other terms are already in the Halak inequality. So using a Halak, I get this inequality. So this is the same as this is tau. So this is a tau 0 minus tau of tau 0 tau, and okay, so minus tau. So this is tau 0 here, r. Okay. Maybe other way around, minus. Okay. I'm sorry. So let me just remind you. So I guess might have to be just a moment about sign. So it's t minus t0. So this then should be plus. Minus plus. That's right. I'm sorry. So this is a minus of this, right? Okay. So here should be plus. Okay. Just a moment. Let me fix the sign here. So that's what I needed. So this is minus, and so if I take h is this, so I minus this term should be plus this term. It seems to be. Okay. Anyway, I think it's I check the sign. So this is So this should be a, is that right? T0, that's a T0. No, I think what I needed is, because T0 is smaller, so this should be a, this should be this. I just got confused. So, so maybe I put this way. So plus, yeah, this is like this. But this is wrong. So because this term has to be positive when the t is sufficiently small. So when the tau is sufficiently close to this, so this should be a plus here, right? Because tau 0 is negative here. So then this is minus this. I got confused. Yeah, okay. So anyway, this is the right term because tau is no. How do I say? So this is minus. So tau 0 is very negative. So this is positive. Okay, so this is right. So tau 0 is so then this is plus, right? Yeah. So then this should be right. Okay, this is term because at t is sufficiently close to T0. T is always bigger than T0 in the Ricci flow parameters. So this should be a positive. This should be very dominating positive term. So it's this. So what I get here should be tau minus t. Yeah. Okay. Fixed sign. So yeah. Okay, so once I have this, so then I know this if tau say is less equal to 1 minus c of tau 0. So for some c, yeah. So I guess okay. So I think this is right. This is so this is come from a Halak. So it has to be t minus t0. And this is okay, or this one okay. So I didn't. So tau, and I think this is right. Yeah. Okay. So okay. So now if a tau is less than or equal to that, so then what I get here is h. Maybe I just leave you to check these numericals. So then this is bigger or equal to 1 over c inverse of tau of r. So R scalar curvature is always positive because we are talking about ancient solutions. Okay. There's other corollary from here. It's from Halak. So I get this estimate. And other corollary of this of Halak is the following. Because this is ancient solution, I can take a tau 0 to be a infinity. Let tau 0 goes to infinity, or this is same as say t0 goes to minus infinity. Then this term is gone because this become the denominator become infinite. So then what we get x to be 0 this time. So I get the dr d tau is bigger equal to 0. Or this is equivalent to say for dr dt bigger than 0. So scalar curvature x t is increasing along the for any ancient solution. For any ancient solution. Okay, so that's good. So particularly if we can bound if we bound, so that implies if we bound the curvature, say if xt0 is, say xt is bounded, then so does of r xt t prime for any t prime less equal to t. Okay, so that's a first step in the halakh. So now I want to derive corollary of this. So this matches well with this reduced length they introduced by Perelman. So if you think if gamma is L geodesic, minimizing L geodesic, then what we know before is we get this function chi c. Okay, this is defined to be a gamma, which in the computation of this the gradient of gamma and so on. So this is given by a okay. So now we bring this estimate in. So we bring in this estimate here. So this will be less equal to bigger equal to a minus of this C inverse and 0 tau bar and the square root of tau, and then the scalar curvature. Okay. Now since this is negative constant here, so this is further bigger equal to a minus C inverse. C is some constant. You can just fixed. Okay, from 0 tau bar of square root of tau of r plus gamma. Sorry, plus gamma prime square d tau. So if you're choosing this is minimizing, if this is minimizing, then this is simply just the C inverse of L x. Okay, so say suppose this is minimizing L geodesic from x. Okay, so then what I get, this is simply the length. So this is the length of at the top bar. Okay, so at the Q is ending point of this geodesic. So this way, what we get is we get the following. So we remember this L 4 tau bar of gradient Lx square. We compute the gradient of L length before. So this, if we recall the formula, this is simply a minus 4 tau bar of R Q tau bar scalar curvature and plus 4Lx. Okay, maybe I just and 4 times tau bar, okay, of gamma. So now using this estimate here, I plug in. So this is less equal to, can find that this is less equal to minus 4 tau bar of scalar curvature plus 4Lx. So then you replace this by that. So this is given by 8 times C inverse Lx. Okay. So now we get a very important estimate. So namely, I divide the tau bar on both sides. So for any tau positive, what I get is gradient of Lx square plus R. R is positive, less equal to some 1 plus 2C inverse of tau of Lx. Okay. So this is a very nice compilation of Halak and together with this new function of Perelman. So we get this estimate. So R is positive. So this is immediately imply that's L square root of maybe square root of Lx square, right? So and 4 times that's equal to 1 plus 2c. C is just some fixed constant. Okay. So that will imply the distance function. So roughly, so of q of at tau, okay, is bounded by some constant like 1 plus 2c inverse of 4 tau, and then the square root of this, then times the distance function, distance at the time tau of xq. Okay. Maybe up to some initial value you start with. So from sorry, not from this, from q to qk. You do. So I do this for any k here. For any k here. So okay, suppose I want to uniform estimate this, I do it for any sigma k. So I guess so apply this to sigma k to gk. Maybe I put k, then I put k here to distinguish. Okay. So the previous estimate is true for any ancient solutions. Now I apply this to this ancient solution in the sequence, because each of these after scaling is still ancient solution. So I apply this. So this is the q and to qk, and then plus this plus L some distance function here. So plus some constant, which depends on depends only on a value of this. Some maybe put this way. So it's some constant, which is some universal constant. Okay, then the square of that. So this constant is just given by some universal constant, and together with the value of this Lk at qk, but which is bounded value. Okay, it's bounded value. So this implies you plug this into here. So apply to here, to each of that. This is as a gradient of Lk square plus R scalar curvature of Gk is uniformly bounded by some constant. Okay, depends only on a tau k of tau. Okay. So maybe I put this way. So at the tau and q tau, q tau is bounded by some constant dependent only on tau and the distance of q tau of qk. So in particular, this is you can take a limit. Okay. So that implies the curvature. So curvature of since curvature is non-negative of Gk is non-negative. So curvature of Gk at q tau is bounded by some constant depends only on a distance of tau 0 of qk and sig tau 0 for for all this tau, that's equal to tau 0. Okay. I'm sorry, for all the tau big equal to tau 0. This is equivalent to all C. The t that's equal to t0 equal to minus tau 0. So why is that? Because here I used this. I used this factor here. Okay. So once I can bound the curvature on a one time slice, then I can bound all the curvature, all the time slices in the previous time. Okay. So this way I can I have a curvature bound. I have a curvature bound and have a curvature bound, so we can take a limit. So by compactness theorem, okay, for of Cheeger-Gromov type or its extension to Ricci flow, I know that so mgk of this qk converge to m infinity, gk, g infinity, and q. Okay. So this is in the C on the m cross minus infinity to 0. So I have to exclude the 0 because all this estimate depends on tau. So tau has to be positive. Okay. So for any time slices before the t equal to 0, I can have a curvature bound. But this bound depends on this factor here. So convergence is only on this part. Okay. So I have so again the convergence means as I said the last time, convergence means any compact set you have exhaustion by compact sets, then that diffeomorphisms from these compact sets to this sequence of manifolds, such that the Proback metrics are uniformly converge to a given one here. Okay. So I have these things. So I have these things. So I have a convergence. So next I want to say limiting is a C infinity solution. So why is that? Okay. Maybe I give you some. So how do I prove this limit is good? So the reason is the following. Okay. So first I have a convergence now. So second, let me the observation. Okay. So if I compute the reduced volume, okay. So first, let's see. So let Vk be a reduced volume for this m, this metric gk from a point, same point of x, okay, which is from same point x, and this point is just a p0 in the m cross m0. Sorry. Okay. So this one here, as we just defined, this is a sigma k inverse. It's kind of like blowing down of original metric. Original metric. It's just a scaling of a fixed metric, So now Vk tilde of tau, okay, if I compute this, so this is by definition is a tau of minus n over 2 exponential of minus Lk of q of sigma k, sig tau, and dq on the n. Okay. But this is gk is just a scanning of that. So this is nothing else but just n. Okay, and we can compute this in terms of original things. So this is just original, this tau and tau k bar. Okay, this comes from a bar, and tau of n minus 2, and so this is let me write this. This is gk. Okay, so then the exponential of minus Lx. So now Lx is original original reduced length, the reduced length for original metric G, and the Q, and the tau k bar, and the tau, so of dVg. Okay. So because all these come from a rescanning of G, so you can just write down by follow the definition. You will see how they scale and these scannings. All these quantity how scale, you will find this, and this is nothing else, just the Vx tilde of tau k. Okay. So I said once I put x here, that means except the one before that. Okay, and so that means this is with respect to a given metric, the metric you start with. If I put a k, that means the quantity computed in terms of rescaled metric. Okay, so now, all these are related to this here, and this is monotonic increase, right? So this will be this is monotonic increase in terms of this here. So that will imply two things. That implies this is monotonic increase both in k and tau here. So that implies the limit of k goes to infinity of Vk tau. Okay, so it's the same as limit of goes to infinity of x of tau k bar tau. Okay, so tau is fixed, and this is same as, since this is a monotonic function, so this is same as like you forget about what the concrete form. You just take tau prime goes to infinity of Vx of tau prime. You rename that things here, but this is a quantity. Let's say it's a V infinity. Okay, so this is V infinity, and this one is a fixed value. Okay, is how do I say? So this one has nothing to do with a k. So this is independent of k here. Independent of k. Oh, sorry, independent of tau. Sorry, because for any tau positive, you can, as long as the k goes to infinity, this thing goes to infinity, you have this unique limit here because of monotonicity. So this is like static constant. So how do I say? It's not a state constant yet, but limit stays as constant. So what's the conclusion here? So first is things. So I know this is always less equal to a 4 pi of n over 2, and big equal, the equality holds if and only if a space is flat. So since the metric you start with is non-flat, if it's flat, nothing you need to do. So this quantity is strictly less than 4 pi n over 2, So that's a reduced volume for Euclidean space. Okay. So other thing you can do is by passing to a limit. So also passing to limit, you get a V as this side once you go this. This is a V infinity tau. Okay. So V infinity tau is defined of m infinity, because you have a convergence manifold of tau of n over 2 of L exponential L infinity of Q of tau and d v g infinity. So this is a constant. Tau here is a constant. Okay. So that's the actual information you get for this limiting metric. But I should say there is some subtlety here. If you pretend this is from the monotonicity and so on, if this is a reduced length for this L infinity, for G infinity, then this being a constant already implies a Ricci soliton, shrinking Ricci soliton. But there are some subtlety here because I only know the convergence. We only know the convergence below the 0. Okay? Because we cannot say a convergence at a time equal to 0. So this is just a limiting function of reduced length. But itself may not be reduced length because G infinity is not defined at time 0. Okay? So all reduced length starts from time equal to 0. But that's okay. So that's so here there are some technical points to justify equations we get. So this stays a constant. So step 3, what I do is we know the following things. Let me copy down the things we proved before. So if you look at the dLk of d tau, there is a differential inequality for each k, and R, this gk plus n over 2 tau, okay, and minus plus lk. I know this is equal to 0 in the sense of distribution. So we can pass to a limit. Okay, so pass to limit. Let k goes to let k goes to infinity. So we will get this. Actually, this needs to be proved. It's not direct because this is nonlinear equation here. You have to make sure even you want to prove something pass in the sense of distribution is supposed to be weak, but it's still you need to do something here. But I will leave out this detail. You can read the book for that. So for details, and this where you get this. Again, in the sense of distributions. Okay, but that's not the end of this. The things I will get is if you compute the volume here, on the other hand, if you compute the volume of dv infinity tau equal along the tau, but of course this is identical to 0 because this is constant. But it just using this formula, you will find that when you compute and this, so this is L infinity, and this thing you will get L infinity d over d tau plus minus the scalar curvature, or I guess minus this, and plus scalar curvature, and then minus n over 2 tau. So that's what you get. Okay. So maybe I leave something here. So then this is tau n over 2 exponential minus L infinity. Okay, so I leave some space here. Okay, So so this is what you get by simply differentiating this. So next, what you do is you can insert Laplacian plus Laplacian L infinity minus gradient. Okay, you can. Why? Because this term you do infinity by parts, it vanishes, disappeared. So it's so you just like add some zero terms. Okay. So then this end thing, this integrand here is less equal to 0 in the sense of distribution here. On the other hand, the total integral is 0. So that you get this is 0. Okay. So let me record one important consequence there. So then what we get is so L dL infinity d tau plus gradient L infinity square minus R scalar curvature and plus n over 2 tau and minus L infinity. This is actually equal to 0. So this is true on m infinity cross minus infinity 0. Okay. So on the other hand, we also have a following. If I compute the recall things, okay, I recall the computation of gradient L infinity square, okay, which is given by minus R, which I already used in the previous estimate, minus R plus 1 over tau L infinity of minus 2k. So this is for k, let's see. Okay. So far only for k. So this is a tau of 3 over 2 of k, capital K, but it depends on small k here. Okay. So on the other hand, I also have a d tau k, d tau, which is equal to R minus tau of L in k and plus half of tau of 3 over 2 of k tau. So now, if I cancel this, because this is something I don't have a control, it's a global quantity. So if I cancel this, I will get identity between gradient, square of a gradient, and the dl d tau. So let me simply write down the things. So this is d. So that implies dl infinity dk tau, d tau, and plus gradient lk square equal to R minus 1 over tau. Okay. So I have some identity. So you can think this is again is kind of clear, because if you think L is simply like an extension of a distance function, it's actually L more precisely is an extension of a square of distance functions. Then of course in the static case you don't have this term. So for distance function, gradient is 1. So that's actually in formula you get. Okay. So once you have this, you can pass the limit, because this is easy to pass. This here is easy to pass the limit because here only involve first derivatives, and I know the L is uniform Lipschitz function. So you pass the limit, I get 2L infinity d tau plus the gradient L infinity equal to R 1 over tau. So also have this identity. So combining this and with these things, so combining these together with these things, I will get a new equation, which I simply write down. Anyway, so maybe I give you can take a break and let me write down. Okay, so it's a some little crisis. So so what I did there is simply cancel these terms. Cancel these terms. Okay, cancel these terms. So we get this identity. Maybe meanwhile, let me. I almost done the proof. I mean, by assuming an identity, which I'm not going to prove. So recall, maybe give you an exercise. So there are some standard fact. Anyway, since we are in that, so this is not right quite in the proof, but let me in the remaining geometry, then some useful and standard fact. I used it myself, and many people used geometry. Okay. So there's some standard fact is following. If I say the M, maybe let's put it this way. So H is a manifold such that Ricci curvature is non-negative. Okay, you can assume Ricci flat, for example. So that's then it's like a special case of standard Ricci solutions. So if you look at the distance function from some point. Okay, so say this is a definition, it's a distance function, say it's a D, okay? It still doesn't work. So the gradient of a distance function certainly is norm is 1. Nothing, okay? So distance function of square O, I mean, then you can easily check. This is what? Anyway, let me skip that. So anyway, gradient of distance function is 1. And by comparison, I know this is Laplacian D is less equal to m minus 1 over D. Right? Okay. Okay, anyway, so then is a fact here is the following. If you know the equality holds, okay, equality holds, then this Ricci curvature actually has to be flat. This is probably not very important. So this is not. What I need is then the manifold is actually a cone. So H is actually a metric cone. Okay. It's a metric cone. So because so the metric cone means basically means a Hessian. So Hessian of a D is special. Namely, Hessing of D is basically one like this. The 0 is the radial directions. Then it's 1 over D, 1 over D. So Hessing, certainly in the radial directions, is trivial. But in the spherical, geodesic spherical directions, is identity. So all we can say, geodesic sphere of this distant, the level surface of this function, distant function, are just has a constant second fundamental forms. So maybe I can leave you this exercise if you. Okay. So basically, what I'm going to do next is try to do this analogy of this in this Ricci flow case. So as you say, as you probably guess, in this case, you need to use certain identities involve Hessing and so-called similar kind of Bochel identities. So here we need to develop some identities here. So let me just simply write down them. I'm not going to prove it because it's a proof. It's just tensor calculations. Everybody can do it once you know what to do here. Once you are giving right quantities. So here I give you right quantities. So M is GT is a Ricci flow. This is general. So sometimes use GT for, maybe I should use GT bar, say. Okay, to distinguish what we had before. It's a Ricci flow. Not necessarily answering the solution. It's any Ricci flow. Okay. So F is a smooth function. So M from 0 T. Here R is a smooth function. So 0 less equal T less than capital T. Okay. So let me form so set tau to be a capital T minus small t. So then so then the U by definition is a 4 pi tau of minus n over 2 exponential minus f satisfies the backward different equations T plus RU. R is a scalar curvature. If and only if this is the first step is easy to check. So dt minus, okay, actually I don't know why I did this, but anyway, so n over 2 tau equal to 0. So that's trivial to check. So assuming this satisfies this equation, so U satisfies this equation here, then the key point is what we're doing here. So then the minus V dt minus plus V plus RV equal to minus 2 tau of Ricci of G plus Hessing of F and minus 2 tau of G square of U, where the tau V is these complicated functions, which actually is integrand of this one functional parameter introduced at the beginning. So this is to U to F, sorry, of plus R is and minus. Okay. So again, I say it's hard to find out such a formula. So once you know what to compute, then it's quite straightforward to do that. Okay. So I'm not going to do in this lecture. I will write whole blackboards and I might get lost in the middle. So the good thing, so you get a corollary. Before I go back to use this to prove that, so let me give a corollary. Say if we define, so this is a functional defined by Paramount. So you can define a function of this way. So say f satisfies this equation, and the g of f and the tau. Okay, it defined to be this integral of this v here with a volume form. Okay, so this is so-called W functional introduced by Paramount. So then what we state here is stronger than. So then the W is monotonic increase, decrease, or increase. Okay, increase. Okay. And the equality holds. G is a solid. Because this side has to be identical to 0. Okay. So I leave you to section 2 of Paramount's first paper. 3, I guess. For details. For more discussions. Okay. But I don't need to use it in a proof boundary conjecture. But it's useful because, for example, you can derive a sublevel inequalities in this way and derive a logarithmic sublevel inequalities and many other consequences. So now let me back to finish a proof by assuming this lemma. So what I did here, so now to finish a proof, take f to be L infinity, right? Then that equation over there simply says that this is identical equal to 0. Okay, so then v is identical equal to 0. Yeah, done. So that implies the solidity equations, the ratio of G infinity. L infinity plus 2t. Okay. So I leave a lemma out. I leave a proof of lemma. Leave out a proof of lemma, and so it's a very nice identity here. Okay, so I think next I certainly cannot give you a full detailed proof, but let me just indicate now in a short time. So that will be needed to classify ancient solutions. So let me state. Maybe which I already stated last time. There's no non-compact non-compact, complete, and shrinking, 2 or 3 dimensional. Shrinking and solidity with so here I say the strictly positive curvature. So curvature strictly positive. Otherwise, of course, you have it. For example, in the 3 dimensions, you can take S2 cross R. Okay, so positivity is needed. Is needed in the theorem. Okay, otherwise you can have a since maybe I just give you an example. So it's necessary since S2 cross R is a solid. Is a just a moment. It's a shrinking solid. With a curvature non-lective. Okay. So let me just indicate what the proof is. It's a beautiful proof, and short of time now. So let me just give you some. So since this is a Ricci soliton, so I know that suppose there's a Ricci soliton, C satisfies these things, a Hessian of F minus C. See, I normalize at t equal to 1, so that let's say this is half of G. Suppose I have a soliton solution. So since I said all these solutions are equivalent to each other for different t's, let's just fix the t at minus 1. Okay. So suppose I have this. I want to get a contradiction in this case. So this theorem may be true for all dimensions. In fact, one of my students made some progress on in a case for 4 dimensions, but he has not been able to rule out. Can rule out certain types. So anyway, so we suppose have this. We're taking a choice equal to n over 2. Okay, taking a choice. So then use the second Bianchi identity and the equation. You can easily get the following. You will get, so for example, you take the second Bianchi identity tells you the following of a scalar curvature. The derivative of scalar curvature is equal to twice of a Ricci curvature, like this. So now use this equation again. Use this equation because this is a parallel. So I get this is twice of Hessian of Ji and J. So now you switch the derivative here. You will get twice of Laplacian f I and minus twice of Ricci ij fj. Okay. Just switch order of derivatives. So the derivative. So then you use this equation here. You will get the identity which says R gradient R equal to twice of Ricci of gradient F. Okay. So you have this formula. To prove this theorem, as we did the last the one for previous one, is in a sense very much look like the something we did in the Riemannian geometry, just in the comparison geometry. So the arguments in the Riemannian geometry was somehow adapted to this case in a very nice way. Okay, so. Okay. So once I have this, I make another claim, which is it's easy to prove, which I'm not going to do it. It's a standard comparison argument. Okay. So claim. So you use the fact the curvature bounded. Okay. I'm sorry. Actually, this is not even. You need that. So let gamma be a air in the minimizing geodesic. Say from a fixed point P, from a fixed point P to somewhere. Okay. So with parameterized with gamma prime to be identical equal to 1. Okay, so it's with arc length parameterization. So okay, so then this 0 of S bar. So S bar is a geodesic on the 0 of S bar. Okay, the parameter space. So air bar is S bar is the length of this geodesic. So this Ricci of x is bounded. So again, x is this, and x is tangent directions. X is tangent. So this is, it's a proof is rather standard. It's you know, how do you prove things like this? Use a comparison. Use the minimality of a geodesic. Then you have some second rational formulas, and you plug in basically parallel vector fields, and you see what you can get from there. So of course, when you do a parallel vector fields, you can take comparison test fields. You need to be vanishing at endpoints. That's easy. You just cut off. That okay. So of course this has nothing interesting if S is bounded. S bar is bounded because I assume curvature bounded. So this is only it's interesting when S bar is very, very long. Okay, very, very long. So I'm not going to do that. That's a standard comparison theorem. So then what you can get from here of another claim 1. Okay. So this is the Ricci curvature of dot x square is less equal to scalar curvature of Ricci. This actually is dimension free things. So this specifies Schwarz inequalities. So here I assume curvature positive. So you just have a quadratic form. You have two quadratic forms. Okay. So anyway, so this is it's like a Schwarz thing. So let me also assume that. So now let's see the consequences of this. So Okay. The consequence of this is following. So then that implies. So that implies the following. So that implies that if you take an integral of this, it's pretty trivial here. Reach of a dot x square of 0 s bar. You integrate along the geodesics. So this will be will be less equal to s bar times the 0 of s bar of scalar curvature times r reach xx. Okay, by this inequality. And the scalar curvature is bounded, so can take out. So this is I'm using this bound. So this is just s bar maybe times some another constant c prime. Okay, c prime. So I mean this is trivial estimate. So now let's see consequence of those trivial estimates. So first I know gamma is a geodesic. Gamma is a geodesic. You can compute the d square of f of a gamma s of ds square. Since gamma is a geodesic, so this is nothing else, just a Hessian of f restrict to x direction, xx direction. So Hessian of f direction, so this is just 1 minus the reach of x, right? Sorry, half of reach of that, because of equation here. I just using this equation. Yes? Here?
Yeah, the reach square.
Here you use the square outside. Yeah. Okay. Square outside, then you use the this get square inside, then you get this. So I have this. So then I integrate this. So I get the following. Once you integrate this, you get df ds in the gamma. So what do you get? You get this at 0 gamma, okay. ds at s equal to 0. This is the s bar, okay. And then integrate this. This is half of s bar over, okay, half of s bar. And then minus these things. Sorry. So this simply means bigger equal to s bar over 2 minus some constant. Maybe just take c to be any uniform constant. Okay. So I am tired of particle c prime, c double prime, and so on. So I have this. And similarly, you can use a second thing. You can take this. So this is like x acting on f, s bar. Okay. So similarly, you can take that E I tilde be say E be any parallel field. Along the gamma, such that E tilde say is perpendicular to gamma, perpendicular to x. So then what you get here is you get E tilde of f of ds. So this is again is x E tilde of f, and this is x E tilde of f minus because this is 0, because E tilde is a parallel field. So this is just a Hessian. But this time it's Hessian in the x and E tilde directions. Okay. So now x is perpendicular to E tilde. So this just have a Ricci curvature comes in. So now I use that estimate in the clamp 2, in the consequence of clamp 2, which I will get this is this will get this E tilde S. No, sorry, E tilde of F. When you integrate of a norm of this along the geodesic is simply less equal to some constant of square root of S. Okay, that's a wonderful thing. So that implies that F is almost like distant functions at infinity. So F is close to a distant function. So close to a distant function, D. At near infinity, near infinity. In particular, there's no also, so this, and moreover, F has no critical point. Near the infinity for S, for distance big enough. Right? Because you always have non-zero vanishings and other directions are small. So anyway, F is a proper function and so on. So other things that you can check is next is I want to claim. So also you have so another case is one thing is claim. Maybe this I can easily prove. So scalar curvature, if it is increases along the gradient line. And that's easy to do because it's easy to prove. See, this is dr composed with gradient line of phi dt dc. So suppose this is a gradient line, say S of gradient line. So this is just R composed dot with gradient of d phi dt, ds, sorry. So this is just a gradient R of df. Because, okay. So now I have these things here. So this is just simply twice of Ricci. So this is strictly positive when gradient for near infinity. Okay, so let me see. So as long as f is not 0. So this is actually strictly increase. Strictly increase. So we are almost done. We need to get a contradiction in the end. We still have a few minutes. So other thing is a claim here. So maybe I just draw a picture. So I have this solution here, say M bar G bar. Okay. So then I have fixed a point P here. So I look at the gradient line of this is in the. So you take a sequence. You take any sequence of a P, say P I, P, and Pj. Okay. Take any sequence. P I goes to infinity. Okay. So then by taking a subsequence, one may have a following. This you take this M bar, and you look at the metric, but you use this Pi as a reference. So now this one has a bounded curvature here. And it's kappa along collapsed. Okay, I always assume that. So injected radius curvature bounded. So injected radius are are bounded from below. So at each point, so this one has a limit. So again, I write as m infinity g infinity of p infinity, because curvature are bounded. Okay. But on the other hand, you think, of course, so this one such that so first, a curvature of that, of course, is non-negative. I mean, I know curvature here is positive, but in the limit, the curvature could have 0 directions, and bounded, for sure. And the second case, because you can think there's a sequence of points go to infinity, and this point is going look at further and further from fixed point. So you can imagine there must be a geodesic line. So actually can be easily proved by standard comparison argument. So there is a geodesic line. Okay, in the limit. So that means it has to split. Okay. So this is the case I use the dimension null now. So it has to split. So okay. And the first is also it's a third thing. It's not flat because scalar curvature is a positive increase. So it has to be along this. You can choose this sequence to be along this gradient line. So the curvature of G infinity is certainly positive somewhere. Scalar curvature is some positive somewhere. Okay, it cannot be flat.
Why is the line and not the radius only?
Because you can think you have a line segment here, and you have a line segment here. You can also have line rate go to infinity. And now you want to do some comparison argument to see you can choose this. How do I say? So
in principle, you get a ray.
in principle, you get a ray. You get like 2 rays. Okay, you get 2 rays. But there is an argument, which actually originally due to Gromov. Is you can choose because, for example, how do I say? Because you have infinitely many points. And you look at the geodesic joining them. So you can think they are since you have infinite many points, you have like countable many directions in the sphere. You can choose a direction. You can choose direction such that the angle are very small. But so then you do some comparison argument. So it needs some arguments here. It's not straightforward. It needs some comparison argument. So you have to choose this sequence in the subsequence in the sequence appropriately, then use comparison, you can get now here. Okay. So there's the geodesic line. So I didn't give a rigorous proof. I only say, roughly speaking, you can think there's a geodesic line because. But anyway, so scalar curvature is positive. So limit cannot be flat, right? Limit cannot be flat. But why is it positive? Because this is increased along the gradient line. So scalar curvature only if it's 0, that means it has to vanish all the time. But I said my space is not flat. Okay. So it's positive. So then the 2 dimension is already gone. Not possible. Okay, because these things will imply these 2 things will imply this m infinity is maybe I put a bar here. Everywhere I put a bar. Okay, m bar is some 2-dimensional things cross with r. Some low dimension cross, and the metric split. So metric split is h plus d t ds squared. Okay. Sorry, I should take a bar here everywhere. Okay, so then 2-dimension case is not possible because if 2-dimension, this is 1-dimension, it has to be flat. Okay, I already said the limit cannot be flat. So only 3-dimensional left. So now assume 3. So assume 3. So far I haven't give you actually conclusion in the claim. So maybe I shouldn't say a claim is a next step, maybe. Okay. So then you because your thing come from Ricci soliton, so it's actually come from Ricci flow. So what you can do is this n is actually it has to be compact. First, the n has to be compact. Otherwise, why n has to be compact? So probably n cannot. So anyway, so I say n h bar. So h bar, n bar is ancient solution. Actually, it's a shrinking soliton. Right? But I just proved the shrinking soliton cannot be non-compact in 2 dimensions. So n has to be compact. So if n is compact, it cannot be 0, it has a positive curvature, then Hamilton, so basically that's what last time I say is the 2-dimensional case, classification 2-dimensional ancient solution is rely on this result of Hamilton in 2 dimensions. Also, so that says this is in the 2-dimensional case, it's just Euclid's field. Actually, this case you don't even need to be a Hamilton case because this is a shrinking soliton. So it's you can simply use a Kasten-Wörter identity to prove it has to be Einstein. Okay, so that implies h bar is Einstein, is of a constant curvature. So in fact, R of h bar, the scalar curvature h bar, by our normalization things is identical to 1. So because of the equation, look at the form of equation you get here. So limit has to be a shrinking soliton. So it satisfies this equation, and it's compact, has to be positive curvature, is S2. So use you can use the Kasten-Wörter, easily deduce this has to vanish. Okay. So how do I say? Because first you can see the F being satisfied this equation has to be a conformal field and so on. Has to be a potential of conformal field. And but anyway, so that's easy to prove. My time is up, so let me just assume that now. So once I have this, so then this is just so things goes to infinity. That's a corollary of this. It's nice. So things goes to this is for along every gradient line. So that says the infinity is basically, so that says the infinity basically is S2 cross R. Okay, so that things the infinity of so near infinity, this n bar approach to approximate to S2 cross R with standard metric. Okay, and this is another thing is you can have is the limit if you go back to a scalar curvature of G bar as the point goes to infinity. This is always identical to 1. And its monotonic goes to 1. So before that, so 1. So and R is checking that's 1. The limit is 1. Okay. So how do I get a conclusion? I get contradiction in 3-dimensional case. I use a Gauss blade. First, I know this scalar. So also of this is the area you check area of each level surface is less than 8 pi. So in fact, this is monotonic. This is monotonic because of convexity here. So you can check and let me make another claim for this. So next claim, maybe 5 now. So let me go back to look a little bit. Good. Okay. So next, what because the curvature is non-negative, so I know this so I erase the okay. So from here, so this is a consequence of this is the following. So maybe I pause it. So consequence of this is very nice now. So that means you look at the Hessian of this f, which is equal to half and minus Ricci. Okay, minus Ricci. So this is bigger equal to, since this scalar curvature is bigger than that, so this is bigger equal to actually strictly bigger than equal to r over 2 minus Ricci. Okay. That's not what I love, I guess. I'm sorry, I do a little bit. So other way around. So then this is less equal to, of course, this is so this is 3-dimensional Ricci. So actually, you can prove, maybe I just do it now. So you can prove this is also less equal to half of. So you compute, okay? So this is 3-dimensional Ricci, then because Ricci curvature is non-negative, and the sectional curvature is non-negative, you can check that Ricci is always less equal to half of scalar curvature. So this is positive. So F is Hessian. So F is convex. So then use the convexity, I get area of a level surface of F inverse C is monotonic increase to 8 pi, because in the limit is 8 pi. Why 8 pi? Because I look at Gauss scalar curvature is 1, so Gauss curvature is half. Okay. So in particular, since it's strictly increased, so this so area of F inverse is less than 8 pi. So on the other hand, you want to use Gauss blade. Okay, you want to bound the things. So maybe I just finish now. So on the other hand, you look at the Gauss curvature by Gauss equation. Okay. By Gauss equation, the intrinsic curvature is of level surface. So you say this is level surface. Okay. So this is given by twice of k, the Gauss curvature of C. Okay, say in the normal coordinates, and which equal to twice of Km. M is ambient space, the second curvature ambient space, plus the determinant of second final form. Okay. So second final form is given by Hessian of F. divided by a gradient of f. So this you can check. This is same as by so r minus twice of Ricci in the normal direction. So E3 is a normal direction. So this is a normal direction. Maybe I put of level surface, and plus determinant twice of determinant. Okay. So where the S is a Hessian. It's a second order form. Maybe I just restrict to this. Suppose this is n there. Restrict the Tn and the gradient f. Okay. So now, so maybe I just get a conclusion. So then you can prove using this formula. You can get Rn. This intrinsic scalar curvature is less equal to R. And anyway, you can check this is strictly less equal to 1 by playing around this element. Okay. So my time is up, so I finished. So that implies this is less equal to 1. So that's a contradiction to Gauss plane. Since Gauss plane says, if you look at this R inverse of C, so this should be 8 pi of. But this is strictly less equal to area. Because of this. Okay. So I stop here. So at the next week, I will, from here, I will list a few property consequences and without proof about ancient solutions. So then I give you a structure of description of structure of singularities. Okay, and so then we do a surgery, try to finish a proof of Poincaré conjecture.